Hi everyone, the first smart material that we'll be talking about today is electrochromic materials. What are electrochromic materials? Simple. Can you imagine turning a pane of glass that's usually transparent, opaque? All you need to do is flick a switch and a pane of transparent glass turns opaque. Don't you want to have your own privacy, but also look out your window at the flick of a switch? That's what electrochromic materials are. How about an example? For those of you living in the west area and take the LRT home, take a look out the window whenever the LRT starts moving. Notice how the windows magically turn opaque once the train approaches the HDB flats? That's an example of electrochromic materials. So how does electrochromism work? Let's start with what it looks like. There are 5 layers in an electrochromic window, like a burger sideways. There is the ion conductor or electrolyte layer in the center, which is like the patty. On one side of the patty, it is the metal ion storage layer, where the metal ions, say lithium ions, sit like the lettuce. On the other side, it is the electrochromic layer where the magic happens. I'll explain later. This is like the tomato layer. Then you have the conductive layers where the current will run, like 2 layers of cheese holding the ingredients together. Finally, you have 2 layers of glass or plastic, which are like the buns holding everything together. There you go, a burger sideways. Now, let's talk about how it works. You guys know what redox reactions are, right? Electrochromism follows the same logic, just that you need electricity to start the reaction. When the current is turned on, the lithium ions in the ion storage layer, or the lattice, is pushed through the ion conductor layer into the electrochromic layer, which is the tomatoes, sort of, where it reflects light away so that it turns opaque. When you reverse the direction of the current, the lithium ions are pushed from the electrochromic layer back into the ion storage layer, making it transparent again. Isn't that cool? Okay, it might be boring, but play along with me, yeah? So that's all I have for electrochromic materials. Let's move on to the next smart material.
Okay, right next we are going to play around with some amazing yet ridiculously messy stuff known as ferrofluid. Ferrofluid is a material that acts like a liquid, yet when introduced to a magnetic field, it becomes like a kind of jellified solid. It is made from ridiculously small, on the nanoscale, dispersed ferrofluid magnetic particles, suspended in an oil-like liquid. The best part of all of this can all be made with simple household supplies. All you need is vegetable oil, around 2 tablespoons, some metal that can be easily magnetized like nails, bolts, a relatively strong magnet, preferably from some rare earth magnets, and last but not least, laser ink toner, those used for printing stuff. This is the fundamental ingredient, as the toner contains the required nanoscale magnetic particles. Also, we need lots and loads of tissues or disposable cloth. Like I said, it gets ridiculously messy afterwards. It pretty much stains everything. Now let's move on to the fun part. Just secure the metal onto the petri dish with the magnet beneath it, use a dropper and position it at the top of the nail, and drip away. You can see how it forms into a dome with tiny little spikes. This is because the ferrofluid follows the path of the magnetic field down the sharp edges of the nail. Given the right surface area, it will spike out. How does this happen? This is due to the magnetic particles lining up with the magnetic field. You can touch it, blow it, spin it, couple it. However, as long as there is that magnetic field, it will remain as the jellified solid. Originally, this was made by NASA in the 60s to control liquid in a weightlessness environment. You can also play around with this ferrofluid in many different ways. You can draw with it, or drop some ferrofluid into a beaker of water, direct it from the outside of the magnet. It won't mix with water because ferrofluid is heavier than water, so it will retain below. Now the rest is just up to your imagination.
Next up, it will be the water-absorbing polymers, which are also known as hydrogels. They absorb aqueous solutions through hydrogen bonding with water molecules. What we have here is called water babies. They reach their original size when soaked in water for a few hours. They can absorb up to 400 times of their weight in water and expand to many times their original size to produce beautiful clear gel-like water crystals. Amazing, isn't it? These water crystals are most commonly used in gardens and farms as they are useful in capturing excess irrigation in any type of gardening or farming. They also help keep the soil moist, creating a healthier growing environment. Superabsorbent polymers also play an important role in the main component of diapers. They absorb and retain under a slight mechanical pressure, about 30 times their weight in urine. The swollen gel holds the liquid in a solid, rubbery state and prevents the liquid from leaking onto the baby's skin and clothing. So, do you want to know how it works? Let's find out. Here, we cut open the diaper and take out the superabsorbent gel. We place it into a beaker. Then we add water. The gel will absorb the water at an astonishing speed and tada! All the moisture is absorbed into the polymer itself. These consumer products include, in order of volume of superabsorbent used, disposable infant diapers, children's training pants, adult incontinence articles, and feminine sanitary napkins.